Get a time check on us here. 10:16. All right, so let's see if we can do this in 18 minutes. All right. So the question of the day is, how do we approximate solutions to differential equations? And already I've thrown a couple at you over the last couple days. Equations like, even simple differential equations like dy dx equals x plus y I gave you the other day. And I said, hey, this looks simple, but it's not, using our technique, it's not solvable inside this course. It's not separable or whatever. So it's very quickly, really, we're almost done in terms of like the techniques we're going to give you. Separable is about as far as we go in this course. So what happens when you come up against a differential equation that you don't know how to solve? And even after you take a whole course of differential equations, it will be very easy for someone to come to you with a differential equation that you can't solve. It's very easy to do. The problem of integration is just a hard problem. So this one is an example of one that you can't solve right now using algebraic techniques. So today you'll learn something called Euler's method for giving an approximate solution to any differential equation. Now, it's an approximate solution, so you won't come up with like an actual function as your answer necessarily. You'll come up with an arbitrarily excellent set of points that represents the function. And just to remind you who Euler is, of course, he's the one that's invented many of our notations that we use in mathematics. And other mathematicians looked up to him as kind of the master of us all, is how Laplace said it. Yeah, so you can read my historical note there. I'm a huge fan of Euler. He's probably I think he's maybe a lot of mathematicians' favorite mathematician, but for good reason. So look at all those notations that you love, that he invented, that we use all the time. All right, so the one thing that we have to say is this is all about linearization. Guess what? It's like the thing we've always been talking about in calculus. Pretend it's a line. So we're just going to do that again. So, and it's going to feel like some other iterative processes that we've used recently in this class as well. You're going to start with an initial condition, like in the warm-up, 0, 1. It's already given. And then we're going to use the linearization. Now this looks terrible, but can you just verify that this is like unit 2 of our course? It really is, right? This is just point-slope form of a line. y0 plus slope times, sorry, this is a little hard to read here, but times x minus x0. Isn't that just the tangent line approximation? Or we called it most recently the linearization. I just don't want you to be on overload because of the notation. It really is just that simple. One thing I want to say though is, why do I have this here? Normally I would just probably say like dy dx at x equals x0. Right? But I have it both ways here because dy dx, just take a seat there. There you go. Because you know that dy dx could look like, oh, I don't know, something like dy dx equals x minus y. It may be that x and y are both needed. Both, in this case, x0 and y0 are needed to calculate the slope. So how do we calculate the next point on the curve? Well, how about we use this formula to calculate the next value, right? The y1, we'll say, is equal to y0 plus dy dx times dx. So what does that actually amount to doing? Well, it's really just saying the next y value, and by next, we have to play a little loose here, up to whatever your delta x is, right? So say you step, 0.5 units to the right. We want to know, what do we think the new y value will be? Well, does it make sense when you look at this equation? The new y value is the same as the old y value that was to the left, except plus whatever the change in y was, right? Does that make sense? That the new y value is just the same as the old value plus the change in y over that interval. So we can continue this iteratively, and this will be what we deem Euler's method. And of course your dx will, in practice, be 0.5 or 0.1, or could be, like it says at the bottom here, it could be going backwards. It could be negative 0.1 or something, and then you're stepping. And each time you're using the slope, you're like basically coming up with a tangent line approximation, find the next point. And from that point, form the tangent line approximation and find the next point. Repeat and repeat and repeat. And you can get arbitrarily good solutions for this if you make your delta x very, very small, you can get a very nice solution curve to any differential equation. So that's the general idea, is what we're about to do, is just use the linearization repeatedly, iteratively. So I know that, like I said, we have to move a little bit quickly here, but so you might not have written down every word on the last slide, but it will be available online. We're going to start with one here today, which, our first example, which is one you could do, so we'll be able to compare afterwards how well this method works, is one you could do already. Why can you do this one, people who did the homework? Because this is an example of a separable differential equation. So we'll use this as our first example like we often do, one that you already know how to do another way, so we can compare how does this actually stack up. And then we'll use it on a harder one that we can't possibly do in our old methods. All right, so what does it look like to actually solve this? Well, it means to get a whole bunch of points on the curve. In particular, it's asking you to compute a y value that currently we do not have. Okay? So let's start writing down the x and y values that we do have on this curve. I'll put it in a box. This was given, 0, 1. Yes. All right, now our aim in life is to figure out what x1, y1 is. And we're just going to form a linearization. At this point, do you think you could find the tangent line to the curve? Even though the curve is not mentioned anywhere, right? But I think we could find a tangent line to it because we have 1 point on our curve, and we can compute the slope on our curve. What is the slope on our curve at this point? What does the slope come out to be? If x is, just a pretty easy calculation at this first point. So y1, we'll call y1 the value of y when x is 0.5 now, which is, in our case, 0.5 units to the left of our first x value, x equals 0. So we were at x equals 0, now we're stepping 0.5 units to the left. I've tried to color code this here, right? So this is just the linearization that I had up on the very first slide. Again, the notation is a little heavy, but do you see that it's just y0 times the slope times dx? That's just, and by dx we mean x minus x0, right? So I hope you see why this together, green times red, gives you the change in y, doesn't it? Now it's not very interesting here. You need to break out all your colored pens too. The original y value is 1, and then we're doing the slope times the change in x. Now as we go through this calculation repeatedly, this will always be, of course, 0.5, won't it, in red? Because that's what we're always gonna be stepping by 0.5. So we'll put this in a box, right? So here was our first x value. Using the linearization formed at that place, we found the next x and y value. Again, not very interesting, because at this first point, the linearization was just a horizontal line. So we said, what's the new y value? Well, it's not a great approximation, but we think, let's just say, because of the slope of that line, let's just say it's the same. You might think, well, this seems like a losing effort. But I promise it'll self-correct in a minute here. So let's just do this again with this result. This is an example, friends, of recursion, right? We're using the previous result each time. So you can hopefully see where each of the blue, green, and red numbers come from. Take a second to verify how I got this next point. The most illustrative thing will be to actually see a picture. I'll draw a picture of this in a minute. You'll see each linearization and how it compares to the actual solution. Anyone struggling to see how I came up with anything in the boxes up there? There's a lot of notation. Point to one of these and tell me, ask me if you don't know where a certain number came from. Y value in blue plus slope in green times change in x in red. Every time. Use the previous result. Let's do it again. And notice that this answers, this finally, after we're doing it, now doing it a third time, this answers the question that was given. The question, let's go back and look, asked us to find what is the y value when x is 1.5? So could we keep going? Yeah, we could. We could just keep going, but it asked us to find this, or like come up with some estimate. If you would like an even better estimate, you could do this in a whole bunch of steps with a delta x of 0.1. Right? It would take you a lot more than 3 steps to get to 1.5. Right? You have the big concept. All we're doing is linearizations. Form a linearization, make your estimate. Form a new linearization, make your estimate. Give you another just 30 seconds to stare at this slide. Make sure you actually understand what just happened. Ask that question. Yeah?
Yeah.
Give me some feedback there. Okay. Alright, that was good. Anyone else have a question before I get off this slide? I want to make sure you understand where every number comes from on this slide. If so, then like most of our work here is done today. We just do to repeat the process. I do want to show you, like I promised I would a second ago, but I'll just tell you right now that if you solve this IVP, which is a pretty easy IVP after some of the ones you've been solving, you'll get this as the solution. That's the actual solution, including the initial condition. You can check if you want. And so let's just compare with how this looks. So do you remember the first linearization we had was just a horizontal line? So there it is. The next linearization was had a slope of 0.5, I think. So that's that segment there, going from 0.5. And notice that we're doing this each time. We're at the new point, we're forming the new linearization. And then at the new point, after we've made that estimate, we're forming another linearization. So you can see that this is like on a scale from good to bad. It's like more on the, it's like bad, it's pretty bad, right? It's not a great estimate. So, which is why we'll move in a minute here, if we can do it, to the calculator and let it do with a step of like 0.1. The same problem we have this kind of coded up. There's nothing special about that what the calculator is doing. It just can do this faster and more of them quickly. You know? So you can see that that could be. It's not bad in the sense that like I see what we were trying to do. You know, like you can kind of see what we were trying to do. It's not as obviously if you have access to the actual algebraic solution, of course that's ideal. But what I'm going to just tell you right now, even though you haven't had a lot of experience with differential equations, is that even when you know tons of techniques, that almost never happens in real life. You usually have a differential equation that you can't like, solve except for approximately a lot of times in life. So here's an example of one which actually does have a nice analytic solution, which I'll show you. But you don't know how, with the stuff we've taught you so far, to solve it. So we'll consider this equation, but it's certainly easy to use Euler's method, isn't it? It's no harder to calculate slopes than it was in the last one. It's easier, maybe. Just subtract x and y. I've given you an initial condition. Actually, it's the same one we had before. We're using a step size of 0.1, and we're going to go to 0.3. So again, this will just be 3 steps, just like it was in the last one. We're not always going to do 3 steps. Here's how you might organize your work, just to quicken your work by hand. And you will be asked to do this by hand sometimes as well, so I need you to be really fluid with the calculator and with this. And we'll make you do it for a couple steps by hand. Like the last one wasn't too bad. We could have probably done that way. So we'll start by writing down our initial conditions, 0 and 1. And then you can see why we're calculating these things. We'll calculate dy dx and dy. Can you verify that those are the numbers you get also? So where do we get dy dx? Say it again, Joshua. Yeah, 0 minus 1 is -1. Yes, good, because he's using that to calculate it. Yes, every time. And then how do we get dy? How do we compute dy? Someone else? Why is it -0.1? Yeah. Right, yeah, take this. And the reason we don't have a column for dx, you're welcome to. You can have a column for dx. It's because it's not that interesting. Every single entry in that column will be 0.1, right? So every time take this column and multiply by 0.1 for this problem and get this column. And then what's the new y value? Again, it's just the old y value adjusted by this amount, right? So now, we now know that the next x value, by the way, you can already populate the first column. It's 0, 0.1, 0.2, 0.3, right? So what's the y value that goes with it? Well, it's 1 plus negative 0.1. Repeat. So how do we calculate dy dx? Good, yeah, right? So subtract x and y. And then multiply by 0.1. Do it again. The second time here. Now the numbers get a little messier. And here's the exact solution using methods that I won't tell you about from differential equations. You can take that course someday. And you can compare how this, did we get this solution, by the way? X equals 0.3, y equals what? It's not actually written up there. We didn't actually say what it was. You don't need a whole line for the last line of the table. It'll just be 0.3, comma, well, I don't know. What is that? Not something real nice. It's 0.82. Can someone do that quickly? I think these are exact values. Okay. All right, on your calculator, let's also solve this problem too. And see if we can do it before you go. I don't know. If you put in y1 on your calculator, x minus y, I know that sounds really weird to do that. But if you put in your calculator in y1, literally, alpha x, well, you normally do that, but minus y, your calculator, this program, it breaks your calculator a little bit. It's not actually going to draft, this doesn't make any sense to your calculator, but to the program, it'll use this, okay? And then run Euler. Once you have it in y1, run Euler. It'll ask you for the initial condition, put in 0 for x, and it'll ask you for the initial condition for y, put in 1. Are we doing this? And then make your step 0.1, right? And see if you don't get the same solution that we got here. Yeah? All right, you got to go. Fine. Homework 3 tonight. Do you still need? Did everyone get it down? Okay. Alpha y. Yeah. Help your friends out doing this. I think on the homework, generally on the homework, you don't have to use this program, but there might be one or two. You want me to put the, yeah, second period. There's no RBC or anything, guys. We gotta. For those who missed the homework here, it's up on the slide here. Homework 3.